Welcome to the one more lecture of systems engineering on the tools that are used in design synthesis. So, the lecture is titled Design Synthesis Tools, and just to recap on where we are today, we have in the systems engineering process we have seen, which is predominantly the US Department of Defense model, US DoD model, where the requirement analysis, then we had the functional analysis, and this was the requirements loop. Then we talked about, from there we talked about design synthesis, and this was the loop between the functional analysis and design synthesis is called as the design loop. And we had another loop which is called as the verification loop, verification validation loop, you can call all those kind of things. And you had the systems engineering process controlling all these. We had seen this model, and we also seen that from the requirement analysis and functional analysis put together, these two together gives us the performance requirements plus functional requirements. What are the functions that are necessary? And once from up to this point, all of these things that we do in systems engineering is the planning for the system. And from there to this point, the design synthesis is there we are doing the conversion of the plan to a final product or system. So, now we were seeing different aspects of design synthesis, and today we are going to see certain tools that are used in design synthesis. There are a lot of tools that are used in design synthesis, but for the purpose in this course, we will be looking at few of them. So, design synthesis, what is it? It involves a lot of tools, and various analytical, engineering and modeling tools are used as part of this. So, why we use so many tools as part of this? The reason being is instead of various, we will use different tools are necessary to address different issues. Okay. So, you require analytical tools. We saw why analytical is necessary. We saw why engineering tools are necessary, and we also require modeling tools. Okay. Then one of the most important one that we talked about is as requirement allocation sheet, or what we call as RAS. We already seen that. Okay. The need of the RAS is to incorporate traceability to functional and performance requirements. So, this means one can trace the requirements to a specific function or to performance requirement. One can trace it and also decomposition from high level functions to low level functions. Traceability. So what does this mean is, when you decompose requirements and performance measures from high level functions to low level functions, then you need to ensure that the requirement is decomposed appropriately and allocated to the appropriate lower level functions. So that type of process is done with the help of requirement allocation sheet, and hence this is also an important tool in design synthesis. Though we said that this is a tool that is important in the case of functional analysis, it is also a tool in the case of design synthesis. So RAS, requirement allocation sheet, is applicable to both functional analysis and design synthesis. In addition to this, which we already seen this tool, we will look at two common tools as part of this. One is called as a concept description sheet, which is normally called as CDS, and then the functional matrix diagram, or normally some people call it as FM. Okay. So these tools, we will see what these tools are all about and what they are and what they are used for, these kind of aspects. So we will discuss in detail about these two. There are other tools as well as what we call a schematic block diagram. Okay. Some people actually call this as SBD. I would recommend that you guys would read about this tool. Another one is CAD, which is computer aided design. CAE, we can talk about it as computer aided engineering. You have CASE, which is computer aided systems engineering, etc. So these are many other tools, mostly dependent upon the advent of the personal computers or high power computing. These kind of tools are quite common as part of systems engineering now. And also SBD is also one other common simple tool. So I request all of you to learn basics about SBD. It's quite simple. Don't need to discuss that in a class. I think all of you are qualified enough to read through that. So the concept description sheet, let's look at this tool as the first and foremost tool that we need to talk about this. Okay. The CDS, the concept description sheet, it describes, okay, it can describe in two ways. It can describe in textual form or graphical form. So it describes either in textual form or in graphical form the technical approach technical approach towards designing the system. Okay. Some people also call this as technical approach. It's also called as the design concept. Some people say, what is a design concept towards designing the system? This is designing the system. Okay. Also, it also demonstrates, records or depicts how the system will be integrated with everything. Why do we need to integrate them? To meet functional and performance requirements. Okay. So, it is quite I usually use this in a graphical format. So, my preference in this game of CDS is a graphical form. So, I will show you a simple example of how the graphical format display of the unmanned aerial system what we talk about. We have been describing this, and so we can say what is the system design concept in this regard. Okay. So, we can say that so here is I will draw, I will try to be like do a good drawing exercise, even though I am not very good at this. So, this is a, we will say, runway. Okay. At one end of the runway we will have what we call as a you would say base antenna, and we would have like a cable running, and we would have like a laptop computer which will be a ground control station which we call as a GCS, and we would have an operator associated with it, right. And then there would be like a UAV. We'll draw it this way. We'll have the propeller in the back. It's flying. It also has a tail boom, something like this. Okay, and here is a UAV. Okay, and it will fly, and there is somewhere here you have a here is a target. Okay, and we can say camera. Okay, visualization, and then this is the communication. Okay, and so we can say that, okay, also we can put like something like a say a generator, something like this. Okay. So, what we can say is that when you show this diagram like this, you can kind of see that it is like a gives you a scenery of the whole system. So, then I can put specifications here. So, I can say that the ground control station, I can put specs as ruggedized laptop with weather protection or something like this. Protect. I can mention certain things also, IP666 or something like that. So, here we will say runway, I can specify things like 50 meters. Okay. Target, then I can always say size of object minimum let us say 20 meters by 10 meters, something like this, right. Then we can also write some stuff like this, that max altitude 5,000 feet, right. Camera, you can always put dual electro optical for day, infrared for night vision. Then you can say the base station, or we call this as the instead of base antenna, we can call it as base station, actually speaking. It's called as base station. And you can say dual channel. Okay. Dual channel redundancy. Okay, now you need to specify what is redundancy for. So, I can always say this, okay, redundant telemetry plus dedicated video. Okay, we can say channel 1 and channel 2, dedicated video channel 2. Then you can specify what is C1 and C2 someplace there. Okay, generator, then I can say this is a 2 kilowatt generator, something like this. Then we can other say user, we can specify what is the name of what's the user, and you can also have like another person here, which is the UAV pilot, who will also have a base box in his hand, who will communicate with the UAV if he wants to. Okay, the communication will run from here to this base box and will be updated. And visualization, what type of visualization we are looking at. Then the UAV, you can put details like maximum takeoff weight, endurance, these kind of stuff. So when you look at this diagram, you can slowly see that you can keep on adding things, but it also gives you a really good input on how the actual concept of the system is described. So the if you don't put the runway, then you will all sometimes people can think that will the UAV will take off vertically, or so now with the runway you know that it is not going to do VTOL. So something like if somebody says vertical takeoff at this point, the question most of the time the answer is no, because you already depicted a runway. Or you would have probably said, okay, if there is no runway, somebody could have said, okay, fine, it could have been a vertical takeoff, that kind of a confusion. And here we said target, the size of the target is specified. So that kind of gives an idea that this UAV is designed to identify a target of this size as the minimum size. I'm just giving examples in this regard. And you can say the UAV pilot, you can put what are the, this is the user qualifications you can add. So what the person should know, how many hours of flying time. Here is the person, you can also say the qualifications, which is the, we can call it as the external pilot, actually internal pilot I would say. Qualifications, other details can be specified. So when you take a look at it, the concept description sheet gives you sufficient information to, so the aim is, that is what we will be writing here, aim, provide sufficient information so that users can understand and appreciate the philosophy behind the design concept. Because this is quite important. The user should understand and appreciate the philosophy behind the design concept, or why that particular technical approach was used in designing that system. So somebody would say, why did you guys use the ground control station as a ruggedized laptop? The obvious question asked here is why. The answer to that problem is why. The answer is the system demanded high level of portability. You need to be moved from one place to another, or mobility instead of portability. Let's call it as mobility as the right phrase. So we will say mobility. So you need to be moved from place A to place B as quickly as possible. So then you have to build systems around in such a way that it can be quickly packed and moved to from one location to another. Okay. Then the second question that somebody can obviously say is that, why did you use two channels for communication? Why do you not? So we can say it's a dual channel. Why did you use dual channel for communication? Well, the customer wanted, so the question here is dual channel this. The question is why? You can answer that, then easily saying that, okay, the people can appreciate that, and no matter what, the aim is to ensure communication with UAV all times. So having a redundant communication in two different frequencies and two different channels ensures you that the UAV is communicating consistently with the base station. Whereas even if the video link we are only given one channel, because if the channel has some problem, the only thing that will happen is you will not get to see the video. That's it. The most important thing at that point, or the importance that was given as part of that design concept or the technical approach, was that the UAV should be recoverable. It should not be a situation where you sacrifice the UAV for the video. So you would rather sacrifice the video for saving the UAV, because you can go back and do the mission again. So that was the design philosophy behind it. So once the people understand and appreciate the philosophy behind the design, then the user will also make amendments to, it's easy to convince the user why a certain approach was used. And a lot of the time, the issues that happens in system design is what sometimes we call as communication gap. So the CDS, concept description sheet, is a good tool that will avoid the communication gap. It will ensure that the communication gap between the user and the designer of the system is minimized. Then we now talk about the second aspect, which is called as the functional matrix diagram. Okay. This is also another important tool that is used by the systems engineers, especially in the design synthesis. And let me explain to you what the functional matrix diagram is. This matrix or a diagram, okay, whatever you want to call it, okay, it helps, this matrix helps to correlate various functions that are to be performed with that of the components of the system. Hence, it is also called as functional physical matrix. The right usage for this is called functional physical matrix, where the relationship between various functions and the various physical components of the system are described clearly in this. So let's take an example of the UAV again, where we mentioned about this, and let's see whether we can actually draw the system. So the first part is we draw the UAV, and as I mentioned, we have 5 components in the UAV. Number 1 is the airframe, and number 2 we have propulsion. Number 3 we have control. Then communication. Last one is payload. So these are the 5 components of the UAV that we mentioned. Now, this is the physical architecture of the system. Okay, here is the physical architecture. Okay, the physical architecture. Then you have to have the functions to be performed. What are the functions to be performed? So let's talk about the functions to be performed when. Let's talk about as pre-flight check. Okay. So there, so then you have different rows in this. The sheet looks something like this, and then we have wherever across we need to do this. So let's say the first thing that we do is check structural integrity. Okay, so what you are doing is you are doing the checking the structural integrity. So you will say airframe and propulsion, those 2 things. Okay, then you will say set home for UAV. So the home is a feature in which if the communication channel goes away, there is no communication between the UAV and the ground control station. It will wait for few minutes or few seconds, actually speaking. It will wait for 30 seconds. And if it finds that the communication has not resumed between the ground control station and itself, then the UAV will assume that, okay, the communication is gone. And what it will do is it will immediately turn back around. The autopilot will decide, okay, let's go back to home. And home is a hard coded point in the memory of the autopilot, which is a place which is somewhere near the, which is typically the runway, same runway coordinates from which the aircraft take off. So you have to set the home for the UAV, then you basically deal with that in the control system, which is the, so the colloquial names for this is the airframe is the airframe, or some people also call this as the aircraft. The propulsion, the colloquial name for this is engine. Control, the colloquial name for this is the autopilot. Okay, communication, this is typically called as comms, and payload is usually the video. Okay. Most of the time people call video as the payload. Okay. So set home for the UAV, it is pretty much part of the autopilot. Then perform communication check with GCS. So the comms will be used for checking that, and there will be also some check on the control also. So that will be both part of that. Then the fourth we will do is check payload functionality. So you are checking whether the payload is working. So then obviously the communication and the payload both needs to be worked, and then you also need to ensure that the propulsion is ready, because you require power to do this. So all these three things need to be done. And then let's say do one more thing, what we call as perform control checks. Control check. Control check is the control surfaces. There are three control surfaces in this. This is the ailerons, elevators and rudders. So they need to be checked. So you need to check the airframe, you also need to check the control, and you also need to check the communications. So this type of a matrix system, where when you doing at each functionality, so these are individual functions, okay, individual functions that are to be performed. So these individual functions are to be performed at some point in time, and once these functions are to be performed, what we do is we take that, and then which are the aspects, the physical architecture, the physical aspects of the system, whatever is relevant to this, we put cross marks on it. So that means these are the parts that are to be used to realize that particular function. So the important thing is that this kind of a tool is necessary because the main thing is that the when functional architecture is transformed or is translated into a physical architecture by using specific physical components, then functions that will be performed by such components are to be clearly identified. So when we say that when we translate the functional architecture into a physical architecture where we use specific physical components, then when the specific physical components are used, then these functions will be performed. We have to decide which of these functions will be performed by such components, and then they are to be clearly identified accordingly. Okay. So, when we talk about this, one of the major things that we need to be very clear about in this regard is how the different components, or how the different physical components that are chosen to build the product will accomplish different functionalities. So, the functional, the right name for this would be, as Department of Defense would call it, the functional physical matrix. Though different books call it a different name, but the most right name for this is a functional physical matrix. It is extensively used by, again, US DoD. I would say this tool was to a large extent developed by the people of the US Department of Defense, and it is also a very good tool in actually identifying which functions are allocated with the which aspect of the which physical component of the system. Okay. Now, before we conclude this, I also want to do a quick recap on something that we discussed earlier. So, now, as I said, when you are synthesizing the design, okay, as part of this, when you are doing design synthesis, you are translating your requirements, whatever is the performance. So, remember that this is where your performance plus functions are translated to a physical product. Okay. So, when you are doing a product development, when you are actually doing the development of a system, then if there is any error that happens in this, it will actually cycle down to the physical product. So, that's one of the other reasons why there is a lot of effort that goes into the ensuring that the performance requirements and the functional requirements, the documents that are part of the loop that we mentioned earlier, okay, or as we go back, this emphasis, lot of emphasis actually goes into this particular loop of the system. So, this ensures that system design is proper. That is the most important aspect of it. And if this is proper, then the design synthesis, okay, if system definition, which is in terms of functional plus performance measures, if these are popular, then design or physical design is also or instead of is will also result in a system that will satisfy the user requirements. Okay. So, by following the systems engineering process, you will ensure that the system is built right and the right system is built. Right system is built. This is the most important takeaway from the systems engineering, especially the design synthesis aspect of it. It is an expensive proposition, as we said. The systems engineering processes are expensive, and there are a lot of other intricalities associated with it. But it also is imperative for all of us to understand why it is so and what are the other aspects of it. So, and we have gone through various aspects, a few tools that are related to it, and thank you for your patient listening, and hope that you will actually learn something out of this course. And in that process, you also, I hope that you guys will apply some of the knowledge that you learned at some places, and you will soon find out that there are so many more tools that you need to learn, and then hopefully you will try to take your career into the higher levels of systems engineering. You will probably get an advanced degree in systems engineering, and hopefully that this course will act as a precursor in that regard. Thank you very much.
get it.
What?
That.
It's a Bradley.
Well, if that's the Bradley, then what's this?
What's the date?
1968. The question is, how did they get to that? From this.
Gentlemen, our mission was to design and implement an infantry transport vehicle that would be a worthy replacement for the M113 armored personnel carrier. We have met that objective and then some. The Bradley armored personnel carrier will bring troops to a combat zone swiftly, efficiently, and safely. It will hold 11 men, plus a driver, and features a 20-millimeter cannon, which will provide ample firepower and at the same time flexibility. Lightly armored, speedy, and solidly engineered, our troops will be arriving at the battlefield in the very finest American technology has to offer. And at $1.5 million per, a real bargain.
Nice work, Colonel.
Outstanding. Damn impressive.
In other words, it was designed to be a big taxi cab, drive guys to the battlefield and go back home.
But how did it end up with a turret on top?
Well, this is all well and good, Colonel Smith, but,
Something wrong, General?
well, with this gorilla in production, I don't suppose there's going to be anything left in the budget for my scout.
Doubt it, Bob.
You don't need scouts. You have radar, air recon, satellites.
You always need a scout. And you know what I'm thinking? Why couldn't this thing serve as a scout?
But it's a troop carrier, General.
But this is a speedy vehicle. Why can't it be both?
Well, for one thing, it's too big. And for the other, you can't really see out all that much from inside.
Sounds like a design flaw to me.
Design flaw? No.
No, we'll just stick a turret on top with lots of opticals.
But then, sir, it'll be even bigger.
Well, what's your problem, Smith? Not elegant enough for you?
Well, the thing is, General, it's kind of hard to do a sneak and peek when you're over 10 feet tall.
He's got a point, Bob.
Well, all I know is we need a scout. This is fast enough to do the job, and it's funded.
Well, actually, we're a hair over budget.
You turn the Bradley into a scout. We're going to be selling them off to some El Presidente de Chimichanga in no time.
Anything for surveillance ends up south of the border before the paint even dries.
When you needed that anti-aircraft gun, who backed you up on that?
You did, Bob.
And who testified to appropriations on behalf of that gun?
You did, Bob.
I'm talking to appropriations next week. Now, do I sell you on my scout or do I not?
You did, Bob. And how about some portholes along the side for individual firearms so the fellas can stick out their guns and shoot people?
Good. And you know what, Colonel? We already have the turret. We ought to get the biggest bang we can up there.
I'm sorry, bang, sir?
You can't hurt anybody with that pansy-ass gun. Add on some firepower.
Where am I supposed to fit the extra ammo?
I don't know. Can't you just shift things around? Make some room.
You already got 4,400 rounds of machine gun ammo. Now you want to add 25-millimeter shells.
General wants his ammo.
You can't have his ammo, not unless he runs alongside this thing carrying it.
Well, can't you just squeeze it in?
No.
Oh, come on, just squeeze it in.
We're not trying on Levi's here, Colonel.
Are you telling me that in a vehicle this size, you can't find room for a few rounds of ammunition?
Not in its current configuration, no, sir.
So the configuration's wrong.
There must be something you can dump.
Dump, sir?
Something you don't need.
General, the interior is very spare. Besides the ammunition and the men...
Maybe you can leave one of the fellows behind. Let the ammo where the men go.
Sir, it is a troop carrier.
So, make a couple extra trips. What's the difference?
They want a transport that doesn't carry men and a scout that's got a cannon as big as a tank's on it.
And portholes.
Oh, great! Portholes. So the guys can shoot out whatever they can't hit with their cannon.
You don't have to buy the damn thing, Jones. Just draw it. That's one hell of a cannon.
That's a problem.
Why?
You go out in a battlefield with this pecker sticking out of your turret, and the enemy's gonna unload on you with all they got. Might as well paint a big red bullseye on the side.
But it's a troop carrier, not a tank.
Do you want me to put a sign on it in 50 languages? I'm a troop carrier, not a tank. Please don't shoot at me.
This was gonna be so beautiful.
That's good work, Smith.
Looks perfect to me.
Thank you, sir.
Thing is,
Yes, General?
looks a little like a tank with that cannon on top. Probably gonna draw more fire.
Actually, sir, that has come to our attention.
We know it's not a tank, but will the other side?
I guess we could always thicken the armor, toughen up the hide a bit.
Colonel Smith, could you explain why you put those portholes there?
Yes, sir. As per your request, so the men could shoot out at the enemy.
You're joking, aren't you?
Besides, portholes? What are we in now, the Navy? Say, you think you could make this thing amphibious? You know, get the troops across a river?
No. No, sir. No. No.
Amphibious? The Bradley's supposed to swim?
In theory, at least.
Amphibious troop carrier / scout.
/ tank.
Couple more months, I bet they can get this thing to fly.
What's this in the margin? Please help me. I am losing my mind. RLS.
Lieutenant Colonel Robert Laurel Smith, head of oversight and development.
Aluminum. This thing's got an aluminum skin.
Huh?
Anything an enemy tank fires at is gonna go through it like a hot knife through butter.
We're doing the specs on using steel rather than aluminum. Of course, steel is much heavier than aluminum, so it won't go as fast.
No, we can't lose speed. We lose speed, it won't work as a scout vehicle.
It won't keep pace with the M1 tanks either.
Thicker armor's a reactive measure. Let's think proactive here. I say equip the thing with anti-tank missiles. Then it can blast those enemy tanks before they get a chance to fire. What do you think, Colonel?
Fine!
Anti-tank missiles?
I don't know.
Where do I put them? The men will have to wear the missiles as hats.
I don't know, Jones. That's why you get paid the big bucks.
Colonel, there's no room. We're not talking
About a
about...
pair of Levi's. I know! God damn it! What we are talking about is 11 years with nothing to show for it. Except an ulcer the size of the District of Columbia and a career that's on permanent hold. You see this? I've been a bird colonel so long, I swear I'm growing feathers. Now, if you have to design hats to hold those goddamn missiles, then just do it. Ladies and gentlemen, if I can have your attention, please. If you'd all just take your seats. Thank you. We are pleased to present a scale model of the new Bradley fighting vehicle. Featuring scout, troop transport, and anti-tank capabilities. It carries 6 men.
How many was it supposed to carry?
11.
Bradley is outfitted with the most sophisticated surveillance equipment ever developed. It is also equipped with a rapid-fire cannon and an anti-tank rocket launcher.
Which means it's loaded with
1,500 shells and 10-tow anti-tank missiles.
So in summation, gentlemen, what you have before you is
a troop transport that can't carry troops, a reconnaissance vehicle that's too conspicuous to do reconnaissance,
And a quasi-tank that has less armor than a snowblower, but has enough ammo to take out half of D.C.
Fantastic.
Congratulations, General Smith.
General?
Hell of a job.
General.
Let's build it.
They're building it?
This is what we're building?